Bismillahirrahmanirrahim. In this lecture, we will discuss the Planck's radiation law. And before this lecture, we already know about the concept of the Rayleigh-Jeans formula and how he explained the low frequency range, and he did not explain the high frequency for the black body spectrum. So due to the calculations in Rayleigh-Jeans formula, there were the ultraviolet catastrophe found, and now we are talking about this Planck's radiation law. So in 1900, Planck successfully explained the spectrum for the black body radiation. So the Rayleigh-Jeans assumption was that the standing waves can exchange any amount of energy with matter. Any amount of energy with matter, and this was the problem. This was the main problem. So what Planck did, he considered that this exchange of radiation of wave with materials must be discrete. So this means that the energy will be nh nu, and where h is the Planck's constant, nu is the frequency, so this will be the integer multiple of this term. So in Planck's in the Rayleigh-Jeans formula, the energy were like this kT, and this shows the continuous amount of energy. So now Planck's consider this energy, and this must be discrete. So the h nu is not the same for all oscillators, because it depends on the frequency of each oscillator. And classical mechanics have no restrictions on this, so whatever maybe this frequency is. So this was also the problem. So this equation E is equal to h nu is called the Planck's quantization rule, and this is a very big achievement. Now Planck assumed that this energy of oscillator is quantized. So we have the Rayleigh-Jeans formula. We already talk about this, that u of nu t, this is equal to 8 pi nu square divided by CQ kt. We have already derived this formula in the previous lecture. So, and from equipartition theorem, the average energy, this average energy is equal to the integral from 0 to infinity e to the power minus e divided by kt. So he used this kt energy, dE divided by 0 to infinity e to the power minus e divided by kt dE, and this is equal to kt. So he just the Planck just replace this integral by the discrete summation. So this is for the continuous energy distribution. So we just change this to the summation. So this is equal to from n is equal to 0 to infinity, and this will show the discrete structure of the energy. So this is minus e divided by kt, and this is summation n is equal to 0 to infinity e to the power minus e divided by kt, and this is equal to h nu divided by e to the power h nu divided by kt minus 1. So we are going to derive this relation. So for this what we will do for this, so we now use the Boltzmann distribution to determine the expected occupancy of modes in the thermal equilibrium. So the probability that a single mode has energy En is equal to nh nu. So this is given by the Boltzmann factor. What is that factor? So I want to write this as E of n, which is equal to the exponential of minus E n divided by kt, and this is divided by from n is equal to 0 to infinity e to the power minus En divided by kt. This is the Boltzmann factor. So this denominator is just for the probability to be 1. The probability must be 1. We also know that. So the mean energy of the mode frequency nu is therefore E nu, which is equal to summation n is equal to 0 to infinity En and probability of n. So we have this probability, so we will use this instead of this. So E nu well becomes summation n is equal to 0 to infinity, and we will write this as it is, and e to the power minus En divided by kt and divided by summation n is equal to 0 to infinity e to the power minus En divided by kt. So we will use the so here we will replace the energy as nh nu in this Boltzmann factor. So this becomes summation n is equal to 0 to infinity, and we will use nh nu here, and e to the power minus nh nu divided by kt. We just replace this energy here and here in this term. This is very easy calculation. So this is divided by summation n is equal to 0 to infinity e to the power minus nh nu divided by kt. So now we are going to simplify this expression. So we will use this as x. Let we suppose this is x. So x is equal to, let x is equal to e to the power minus h nu divided by kt. So this is now going to easy. So we will just put x here and x here. For this, this e nu will becomes the summation of n is equal to 0 to infinity, and I will use this nx to the power n divided by summation n is equal to 0 to infinity and x to the power n. And if we let out this h nu outside, so I will use this here h nu. Now we are going to put some other relation here. This e nu is equal to this. So if I use this relation for n is equal to 0, so the answer is 0 here. So 0 multiplied by x to the power anything, so this becomes 0. But if I use n is equal to 1, so this becomes x. So I can write here, this is h nu. So we are going to expand this series. We just use the value for n is equal to 0 here. So we got 0. Now for n is equal to 1, so this becomes I can write as this becomes x. So this is plus. Now if we use n is equal to 2, so this will become 2x square plus if n is equal to 3 and so on. So this will become 3x to the power 3. So this plus and this so on. This is divided by, if I write the same for this, so we will get 1 plus x square plus x cube plus and this. If we look here, this x to this x here down, so I can write this is a little different way. So we can write, can change this a little. So this is E nu is equal to, let x common from this equation. So h nu, I take if x is taken out from this, so this x come here, so I can write this is 1 plus, so x from here, so this will become 2x plus this will become 3x square. So x is taking common from this all and plus this. So this is divided by 1 plus x square plus x cube. Now if I look to this, if I take the derivative for this, so x, the derivative of x d divided by dx, which is equal to 1, and for this 1 is 0, so we did not write it here. And if we look to the derivative of x square, so we know that d divided by dx x square is 2x. This is 2x, and if we use the look to the derivative of x cube power 3, so the derivative of x cube is 3x square. It means that this is the derivative of this expression. So I can now expand this series, like I can say that 1 plus x square plus x cube and plus so on. If I write that this is equal to 1 divided by 1 minus x, so this is also true, because if I use this 1 in x, so this is 1 minus 1 and 1 minus 1 is 0, so this can become 1. If I use x here, so this can become x, and we can expand this whole series as this formula, and so on, as we saw here that this is the derivative of this function. So we can write this d divided by dx 1 over 1 minus x. So when we differentiate this, this will be equal to 1 divided by 1 minus x whole square. Now I want to put to use this relation, these two relations here. So this will become E nu, which is equal to h nu x, and I can write this as 1 minus x whole square, as I found this here, and this is divided by 1 over 1 minus x. So this can cancel with this, so we get only E nu is equal to h nu x divided by 1 minus x. Now I can write this x divided by 1 minus x like this. This is equal to h nu divided by x power minus 1 minus 1. This is also true. We can write this as like this. So this x came down, so this is minus x, and this is becomes minus 1. So this is very easy mathematics. Now replace the value of our x here. If we already let that x is equal to e to the power minus h nu divided by kt. So this is x. We will use the value for this here. So e nu, this is equal to h nu divided by, if I use this value for x, so this is minus minus plus, so this will become e to the power h nu divided by kt, and this minus 1. So we derive this relation we already discussed here, this relation, not this one, this relation. We derive this relation here. Now what Planck did here, Planck's from Rayleigh-Jean's law, the number of modes in the frequency interval from nu to nu plus d nu, we know that this is equal to 8 pi nu square divided by cq d nu. We already calculated this in our previous lectures. So it means the full form of this is nu d nu, which is equal to 8 pi nu square divided by cq, and this is e nu d nu. So we will use the Einstein relation here for this energy. So we will get this u nu d nu, which is equal to 8 pi nu square divided by cq, and for e we will use h nu divided by e to the power h nu divided by kt minus 1, and this is here d nu. So I can write this expression like this. So this become u nu d nu, which is equal to 8 pi h, and this nu and nu square becomes nu cube, and this is divided by cq. So this will become 1 divided by e to the power h nu divided by kt minus 1 d nu. So this is called the Planck's radiation law. He successfully explained this curve, this observed curve, this experimental curve. So how can we know that this formula shows that he explained this curve successfully? So we will derive the Rayleigh-Jean's formula using these relation and the Stepan-Boltzmann law and Wien's law from this calculation. So if we are able to calculate the Rayleigh-Jean's formula and the Stepan-Boltzmann law and the Wien's displacement law from this equation, we will use this equation. So we will get the for low frequency and for high frequency. So this means that Planck's radiation law has successfully explained the spectrum for the black body radiation. So in next lecture we will see that how this equation can uh, can go to the lower frequency and higher frequency.